Hi, everyone. Welcome. My name is Himanshu Singh, and I'm an engineering manager at Netflix. And with me, I have my colleagues Rajeev and Jayadev. And today, we are going to talk about how we are scaling Netflix knowledge graph with LLMs. But first, let me briefly introduce what this Netflix knowledge graph looks like. At its core, this knowledge graph is made up of hundreds of millions of relationships between many real-world entities like movies, cast, books, and many more. And then relationships include things like directed by, acted in, distributed by, and many more. The data comes from multiple sources, and it is used to build a graph with many entity types and relations, thus resulting in a dense network of nodes and edges. This network of nodes and edges, as well as the semantic information captured in this network, is then converted to low-dimensional embedding vectors. And then together, the raw knowledge graph, as well as the embedding vectors, are used to power many different scenarios within Netflix. Things like content understanding, where we would try to understand what our movies and shows are about, enabling better predictions, and then providing more accurate and intelligent search and recommendation results. So in a nutshell, the knowledge graph helps us in building a much better understanding of entire entertainment landscape. Now, let's quickly look at how we were generating this knowledge graph traditionally. The knowledge extraction would take place from many structured data sources. So these structured data sources would then be mapped to our own internally defined graph schema, where it would include a lot of traditional transformation ETLs, uh, where we will create these graph entities and relationships. Now, these separate entities coming from separate sources are then matched and merged together using our entity matching or entity resolution frameworks. Then we would enrich this graph using graph inferencing, where we would derive additional knowledge on top of existing data. And finally, we would prepare this graph for serving to our consumers through ways like graph APIs, uh, graph queries, and pre-computed graph walk tables. Now, in next few minutes, we are going to talk about how we are scaling each of these components using LLMs, what challenges we are facing, and how we are trying to solve those challenges.
So, the first component which we are going to discuss is how we are improving the completeness of graph, or you can say the coverage of graphs using LLM. Uh, First, we will go through a set of challenges which we were having earlier, and LLM has shown a promising directions, and then we'll go on the 101 pipeline for one of the components. So first, in our case, let's suppose this is a title which is very sparse and just have a name. And our no, we but from if you see from the title name, we have a Chiefs versus Steelers. So our goal is to connect this to actually the team entities, which is Chief and Steelers. So earlier it was quite challenging, but LLM has shown much promising directions. Similarly, another example, this is a title which is very sparse plot summary. And also if you see that mentions are completely mixed. And our goal is to connect these two again, two different entities, which is a team. So mixed entity mentions, and still we want to achieve this. The second is like always the multilingual was always challenging. And that's also, we have to always do some special things to handle multilingual. But for example, these titles, there are two important persons connected with Michael Sons, and which we want to connect. And multilingual plot summaries are here. So LLM is also showing promising directions on this. The another example is always the fiction titles are always quite challenging because the mentions names are always ambiguous. For example, if you see Dr. Pretorius or Dr. Frankenstein's, these people could be people, but actually in a real, in a this fictional world, these are characters. So identifying and disambiguating these types of mentions is quite challenging. And again, here the LLM was showing promising directions. Another applications like we know a lot of movies are based on books, but we really want to understand more depth about book, whether this book is novel, whether this is a short story, or whether this is poetry, or even a much more depth level. So semantic tagging is another application. Shows good. Another is just like type classifications. This I will quickly go. Like if we do more type classification better, then entity matchings become much better, improves the quality, and that's another. So like here, if we really do the type classifications properly for this graph entity, which is available in our systems, then the entity matching accuracy improves. So with that, I will go through one pipeline, how we are doing it, and what are the few learnings or how we have handled it. So we take title this pipeline. So what we do is, and that's where the biggest mm, promising direction we got is entity direct extractions. So earlier we were having just a small mentions informations, but with LLM we have much more context about entities, and not just one entity. We can get n number of entities, which will help in down component to achieve precision and recall. So for example, this we can get like whether the chief Steelers is a American football team or also rugby football teams. So once we have a information extracted in a much richer with richer context, then we have already a scalable and entity matching pipeline through which we do the linking. And once we have that linking, there is another step because there is always possibility that extractions will have error or hallucinations. And that's where that LLM verifications as a judge comes, where once we connected the entity to graph, we can put much neighborhood informations from graph and then ask the LLM that whether the extracted entity is really makes sense or not. For example, if I give a Steelers rugby team, but from neighborhood informations, this will say that, okay, the Chiefs is not connected to this, then they will say no. But if I give football team from a neighborhood informations, then it will say yes. And with that, because once we connect it, then we can infer the relationships. So this is a one component, but similarly for all semantic tagging or for tab classifications, LLM has shown promising directions. With that, I think Jayadev will go one depth on another component, which is matching. Yeah.
Hello. So this sets up well for the next piece, which um, luckily this is one stage where most of you are aware of because I've heard this from many people. So that is the entity matching part of it. In many of these talks here, we refer as entity resolution. And how can we scale that? And why do we have a unique challenge with this, especially when we are trying to build a graph from many different sources and getting it all together? And precision is very critical for us. So very quick, a high-level intro slide, which this group doesn't really need it, but just to kind of make sure what we're using the same terminology. Entity matching, as you can imagine, it is just how can you identify entities referring to the same real world entity. In the point I'm trying to drive here is in the case of shows, and movies, getting it correct and very precise is very critical for our predictions or any kind of analytics, because as many of you know, like Game of Thrones, from one season to another season can make a big difference. So you might have similar directors, similar actors, but the interest in the show could be very different. And we need to kind of really capture that very accurately. Similarly, there might be some slight variations in, say, a poster in this case, but we really need to know that they are actually referring to the same show, same part, same episode, and that detail is very critical for us. So identifying this is one of the core challenge, and then you can from the show you can build the entire universe of entertainment from there. And one more quick slide on the key challenges we face. For example, in the world of entertainment, there are like the limited terminologies and topics that people kind of work on, and there may be very similar names. In this case, you can see the two movies which are same genre, similar release year, but one has like 41,000 reviews and one is like hundreds. So it's like very different shows, and understanding that is very important. Same with different kind of topics, and some topics are universally so appealing that you always see a movie or show in the world somewhere made with a similar topic, even with similar directors sometimes, but you still want to differentiate it. So I'll call out three key challenges that we typically face. One for us is, in our case, it's a large knowledge graph with many, many sources across the globe. So even to compare all the pairs, even with millions and hundreds of millions of entities, it could go to billions of pairs that we want to compare. So efficiency is very important to us. Second is operability and ability to kind of expand and debug that. I'm looking at time. Okay. Expand, debug, and all that's been very critical for us to kind of make this work. So when we try to extend the system, we are very keen to understand that whatever system we go with can actually solve this. So this is as Rajeev mentioned, early work. We are all, like, I think many people in this room trying to figure out how these powerful models can be tamed for our use cases in a reliable way. So I picked a couple of directions we have been exploring, and some of the challenges we are facing and the results. So one, the most simplest question, these are powerful models. Why don't we just directly give this entity the metadata and match it? And I actually already heard some of the teams here which already trying to do that. And it's a very appealing thing, and some people are already shaking their head, so who have tried it. But the promise is very appealing though. So we should call that out. Like if you are used to a normal ML loop, uh, then you can see that typically something like this actually requires us to get training data, ground truth, go through the whole loop of tuning it and all that. And now here is a model which is saying, you know what, I can, with few shot, I can give you a out of the box model to work with, which is very great when you want to expand to new entity types. It reduces the time. Semantic understanding in a typical ML model, we spend quite some time to get the semantic models work fine, understand languages, nuances. And also world knowledge can be leveraged. So it's like seems like a very interesting proposal to kind of try it. And the challenges that we all have is to make sure that will it really work with high precision? Can it work with structured data in our case? Because many times we spend a lot of time, extracting the data in a good structure. And can it work for at scale for large data sets and with the precision we want? So I'll call out like a few examples to the things we have learned in the process. And I picked, like, it's a big presentation. I picked like few examples of the key learnings. One simple example here is, if you see these two movies, a human can look at it and say that, you know what, these two are same movies. But an LLM on an initial prompt might say that they are not same because the release years are actually 2 years apart. And the key interesting bit is very obvious for most of us, but a simple prompt update, you're surprised for a normal ML engineer that a prompt update can immediately, it can catch and immediately correct it. Now, what else it does with it is something which you have to still figure out. But this becomes like, oh my God, this is what the new parameter tuning might look like. So that's an interesting promise. But more interesting bit is the explainability that it brings in. Look at the way it kind of describes why it made the decision and how it can change our understanding of how to improve matching. Now, another case is list. We deal with a lot of lists. In this case, cast. The order could be different. The names could be slightly different. Can it catch all those nuances, right? So in this case, it can. So it kind of, it's agnostic to all that. It agnostic to the names. So it kind of understands all that. So it's a really a powerful model to deal with kind of structured data. And another example would be, in this case, I'm dealing with cases where, names are slightly different. The movies feel like they are different. But if you add description, it's a very powerful feature where it's very clear that they are referring to the same movie. Now, the question is, typically, again, put your ML engineering hat in the previous days. You will have to kind of encode that and embed that correctly and then tune it or fine tune some of the large models and do that. And here, again, adding a multimodal or a dense feature is, just summarizing and adding it, and potentially it just picks on that. So for example, just adding description, it kind of picks the fact that, the description enables it to match. So just to drive home the point that, it brings in explainability, it makes it easy to extend, it is very powerful in understanding many of the nuances that we typically struggle with a syntactical model or with our typical ML engineering. Now, of course, Nevertheless, any solution comes with its own side effects and problems. This is something that we all as a community have heard again in multiple talks here that we struggle with, that now we are dealing with this giant prompt instead of matrices and the features that we used to deal with, and how sensitive that prompt is. In this case, we have to realize that just changing the question from top to bottom changes the accuracy. How verbose the prompt is makes a difference. Then how you encode the strings, especially with multiple language. If it is a different language, do you just put the string there, or you do put the encoding if you are aware of it? And that makes a difference in the precision of the model. So now you are in the world of understanding and fine-tuning this and managing that very carefully. So that's obviously one obvious challenge that this brings in. And then the other one, and it's a very quick take on, we have a very curated duplicate data set, which is tough to kind of classify. And we did a run on this using our, whatever the fine-tuned prompt that we have. And you can already see the very obvious conclusion that powerful models matter. Even though the problem feels much simpler, still a powerful model or an expensive model does much better, which actually means that we really have to now figure out the trade-off of cost versus efficiency too, in this case. So we cannot just throw in a simpler model for this problem. So few quick takeaways. Many of this I called out during the slides about explainability part of it, the richer semantic matching which comes out of the box without all the hard work that we normally do, and powerful models being pretty good at this. But if one thing that if you want to call out is I did a back of envelope calculation with the kind of decision tree model that we use, and it is much slower and way expensive. You're talking about 2 orders of magnitudes or multiple orders of magnitudes difference, which actually means that it's a real trade-off that we all need to kind of really consider. Now, very quickly, I will go over that with that particular knowledge about the cost and speed. There is one idea that we're exploring, which could be a middle ground for many of us to try. That is, why don't we not change our model itself, but what if we introduce it as a judge? So think of a human annotator that we have, where we do the matching, and all the problematic matching we can show it to that annotator to kind of get a better idea. And can we do something similar with LLM and kind of fine-tune that process? And that could kind of scale some of these efforts, right? And you don't have to change the core model. You can use existing model and then start fine-tuning it. And this is also a simpler alternative because, again, as I said, it's less disruptive to your pipeline, much cheaper because you're not going through the entire process through that. And you can also introduce complicated semantic features there instead of, in the model itself. And this process actually can add explainability. So you think of the loop there. It'll add explainability. It can kind of fine-tune the process from human and then kind of, make it better and better. And we can scale this whole process of how much we can judge in this case. So a final slide on this is the challenges. Again, this is still, remember, an expensive call. And how it will hit you is sometimes there is a sudden source with, say, instead of 1,000 entities, a change, there are 20,000 entities. And that it suddenly can skew the pipeline because many of the LLM calls are throttled. Cost variant is there, and suddenly from 20 minutes, the pipeline go to 4 hours. So you have to be very mindful of the cost still and how to parallelize it. Then it's a powerful model. This prompt, I've not shown it here, but we can talk about it offline. It's even more complicated prompt to compare the entities. Now, comparisons involved and how to fine-tune it, how to shape it is actually a research problem itself. And the challenges to be we have to be very mindful about, and all kind of new biases that this paradigm brings in. Very simple as position bias. If you're comparing 2 titles and you ask it, is A better than B? You change the order, its decision will change. And it's very interesting to see how the distribution changes with time. So it's very critical that we are mindful of the position bias, verbosity bias. We add more detail. Sometimes it doesn't pick on other features. And sometimes self-enhancement. If you use a particular LLM to match and use same LLM to judge, it tend to think that, it's better. So, we have to be very mindful of these aspects when you look into it. Now, with this, I'll hand over to Himanshu that think about it. Once you extract, you match, now you serve. Can LLM help in scaling the serving process too? So I think Himanshu will talk more about that.
Okay, so far we have seen how we are leveraging LLMs in graph generation or graph construction phase. But we also face challenges in graph serving because many of our data consumer teams are business stakeholders, and answering those business questions by writing graph queries against graph database is not always easy for those consumers. So we are working on providing a natural language interface to answer such questions for those stakeholders. To dive a little deeper, let's say someone at Netflix will ask a business question which is related to our content or data. To answer the question, we will use our knowledge graph as a RAG. So our knowledge graph is stored in a graph database, and we will also store the low-dimensional embedding vectors in vector index. Now, based on the question, we may need to select right set of tools and sources to route and get the answer. Now, this may mean that we may have to do a semantic search on our vector index, or the tool could involve querying, like converting the question into a graph query, which is then executed against the graph database, and the response will include a list of relevant nodes and edges. Now, all of that information is collected and presented as enriched context to LLM. And LLM then merges this information with its previously trained information to produce the answer for our consumers. Now, this is an active area of exploration. There are different sort of challenges, like how we efficiently convert the question to a correct and efficient graph query. How do we select the right tools? How do we select the right sources, and so on? And we are actively working on solving those challenges. Okay, a very quick recap of the entire presentation. So, so far you have seen that with LLMs, we are now using unstructured sources as well as structured sources, unlike before, where our graph was mainly built using structured sources. We are moving our knowledge extraction pipelines from traditional schema mapping and transformation ETLs to LLM-based extractions. We are augmenting entity matching with LLMs. And in some cases, we are doing matching directly using LLM. And in other cases, we are using LLMs as a judge. We are moving from rule-based inferencing to LLM-based inferencing, where we are doing things like semantic tagging, entity type inferencing, where we are trying to identify what type of entity it is, and so on. And finally, we are moving our graph serving stack from traditional ways of APIs, graph queries, and pre-computed graph walks to more of a natural language interface. With that, I'll conclude our slide and happy to take questions that you may have for us.
Thank you very much. I will start with a question. How do you build the embedding? You didn't say what sort of techniques you're using for the embeddings. Can you say a few words?
Yeah, Jayadev, you want to take that?
Embedding, right?
Yeah.
Yes, that's one of the slide actually I removed due to lack of time in the matching. Still an area of exploration, but if you look at it, in the case of matching, I just showed you prompt-based. The other idea is we are trying to take the embedding itself of the entity and then try to find candidate pair using that. And then also see whether that could be used as a feature in our matching. Like as I said, the matching side, just removing that and completely replacing the LLM is expensive and has its issues. But we are trying to see a middle ground where we can use the embeddings kind of, at least for candidate generation to start with. Again, there are challenges there with if there is a huge text with like description, it can dominate something very important as like a director name or a movie name. So we'll have to kind of balance that. So we are trying to figure out how the right balance could be. So, but that's how we are trying to attempt using embeddings.
Okay, thank you.
Excuse me. Thanks. You went kind of rapidly on that slide, sort of the results slide, where it seemed that you said that we did this LLM matching and it was orders of magnitude worse and worse results. Was that the actual conclusion?
Next, I think next.
Not that one. I think it was the next. Yeah, there you go.
Yeah,
Is
yeah,
that it?
yeah. No, that is not the conclusion. It is like we tested for a, let's say, sample data set initially.
Yeah.
And we were just trying to see the promise of the approach.
Yeah.
And we find that for entity matching out of the box, it does bring in a lot of promise. As I said, all the semantic language understanding and all that is promising. And did a back of envelope calculation to see what it takes for us to, if today I were to replace my entire current ML model with LLM matching. And that is order of magnitude expensive.
Yeah.
So, which means we will have to invest more. It's like an indication that we'll have to invest more on either fine tuning a cheaper model, or we will have to do some kind of caching to make sure that we do the LLM based matching only for special cases. So some kind of optimization is required than just throwing our billions of entities into it. So as of now, it is very expensive to
Yeah,
replace.
it's a great experiment, but I'm curious why you're continuing on with it. I think you demonstrated that it's not promising.
No, that's not true, because we have now, like, for example, this is what even led us to the LLM-as-judge kind of approach, where we use a traditional model to kind of do the matching, identify the special cases where it is in the threshold limits, which we are doubtful about, and then bring in LLM at those times to kind of do a second review. So it could be a process which, like, where we can add more features also into that, more richer features. You can even add image or description to that. So it kind of shows the promise of it, the places where it can be applied. So we are not taking it away from the system. We are still think that's very promising, but we have to be very mindful of how to balance the cost. And also, I think this is the cost when we use like very expensive models. Models are going to get cheaper. We could use a Llama model and fine tune it. So there are a lot of opportunities there which has to be explored.
My question was actually related to LLM. You might have answered this just in the last 1 minute, but just to make sure, for LLM as a judge to do what you want it to do, you have to pass the context. So the idea that you couldn't pass that in the first place, is that pure system performance, or is there some other reason?
First place means in the model itself.
In the original matching itself, you could be passing the same context.
Correct.
And asking, just give me the right match.
Right.
As opposed to
Right.
having it match and then saying, I'm going to give you additional context and tell me whether it's the right match.
Having it match. So in the current case, imagine you have an existing matching model that in your system, right? Now, that may not be using all the latest features. Like, for example, if you want to add image or description into that, that is a complete ML loop that you have to go through. Get the data, train data, you know, the typical loop, right? So that I could do and go through that, but this might provide a very quick way for me to introduce all the other metadata, even if it's sparse, into the system, and still use that as for judging before I can refine the model altogether.
Okay, that makes sense. I guess you're not seeing any difference in LLM behavior. I'm trying to get at that as to when you pass it, right? That's not the reason why you're...
No. That's not the reason. Yeah.
Okay,
It's
thanks.
like as a judge, you give a entry point for more features.
Understood.
By the way, I know we are running out of time. We'll be here. Catch us on the hall for any other questions.
There's one more question.
One more question, if you're okay with it.
Thank you. Great presentation. You mentioned inferencing, and I'm used to that being in the context of things like a data log engine or OWL reasoner or something. Can you say a little bit more about how you do inferencing?
Yeah, so does it mean that tag inferencing or type inferencing? So we do 3 types of inferencing, as mentioned, like one is like inferencing the relationship, which we show in a pipeline, that we know the entities and we wanted to connect to other entities, like for example, given title to connecting to the existing team entities. So that's inferencing we do, and but also we do type and tag inferencing. So which one you want to, like, any specific one inferencing you?
That's okay. I know we're probably at time, so I'll find you outside of
Okay,
the
sure.
talk.
Okay.
Thank you.
Thank you.
Thank you all again.